Hello, calculus students. This is my first video, and this is covering section 4.1 on related rates. You can find this handout on the blackboard for our course. And what related rates is about, what I say here is if we can find an equation relating two or more quantities, then by taking the derivative with respect to time, we have an equation relating the rates or changes of the quantities. Now, what this is about is if one thing is changing with respect to time, then many times there are things related to that changing object, and you can compare their rates of change. So let's just take a look at some examples here. Number one, when the diameter of a spherical tumor is 16 millimeters, it is growing at a rate of 0.4 millimeters a day. How fast is the volume of the tumor changing at that time? So notice that we're looking at a spherical tumor, and we know the diameter is 16 millimeters, or at least grows to a point where its diameter is 16 millimeters. And the rate it is growing is 0.4 millimeters a day. And we want to know how fast the volume of the tumor is changing at that time. So it, of course, is getting bigger as the diameter increases. Then definitely the volume is increasing, but by how much? That's the question. So I've written a few things before filming. Again, this is 4.1, number one, and I've drawn a sphere, and the sphere has a 16 millimeter diameter, and we know that the volume is increasing as the diameter increases, and we need a relationship between volume and diameter. I wrote this down. The diameter was 16 millimeters. At that point, we want to know what the volume change is, and we're also given that dd, I'm using capital D for diameter, the rate of change of diameter with respect to time is 0.4 millimeters a day. The relationship I know with volume and diameter is volume and radius. That volume is equal to 4/3 pi r cubed. And I want to change this so it's in terms of diameter. And I know that the radius is half the diameter. So what I'm doing is rewriting this volume equation by substituting in the relationship between r and d, which if I put in 1/2 d here and cube it, then I get 1/4 pi, and then 1/2 cubed is 1/8, and we get d cubed here. And our volume is equal to 1/6 pi d cubed. So this is a formula of volume with respect to diameter instead of with radius. So that's what I wrote here. Volume is a function of diameter. And now I have a relationship between volume and diameter, and now I want to take the derivative of this with respect to time. Now, if you recall my operator, this one right here, this was my d. I would take the derivative of something with respect to x. And now what we're going to do is take a derivative with respect to time. So this is my operator. I'm going to be applying this to both sides of this equation. So you'll see in the next step that that's what I'm doing. I'm applying d dt, that operator, to the v and to this 1/6 pi d cubed. And when I do that, this I'll just write as dv dt. That would be the change of volume with respect to time. And here I'm going to factor out the constant 1/6 pi, and then take the derivative of d cubed. Well, what's the derivative of d cubed with respect to time? It's 3d squared, but then you have to do chain rule, and you end up with that dd dt. We did this when we did implicit differentiation. Whenever we had a y, we always had to write dy dt. Well, in this case, you have to take whatever the variable is, like v, and that has to be written as dv dt, and now I get 3d squared d cap d dt. And I'll simplify that. The 3 and the 6 cancel. You get 2 in the denominator, and I have 1/2 pi d squared dd dt. So this is a relationship between the rate of change of the volume with respect to diameters change. So we know that dv dt is 1/2 pi d squared dd dt, and they want to know what was the question? The question was, how fast is the volume of the tumor changing at the time when the diameter is 16 millimeters? So what we're going to do is substitute in 16 here, and ddt was given. It was given, I wrote it up above, as 0.4 millimeters per day. Be careful of your units. This is diameter is measured in millimeters, and time is measured in days. So if I substitute in my values here, I get 1/2 times pi times 16 squared times 0.4. I multiply that, leaving pi. I'm not sure if WebAssign is going to ask you for it in terms of pi. And then if I plug in pi, I get about a 160.8. Now this unit has to match this. So dV, volume, is in cubic units and time is in days. So this is going to be cubic millimeters per day. And I wrote, when the diameter is 16 millimeters, the volume is increasing by 160.8 cubic millimeters per day. Now I do have a note up here, a note on units. Sometimes in some classes they have you put the units into the equation. I usually don't, and I just give the units at the end. But when we substitute in 16 millimeters squared times 0.4 millimeters per day, and I just look at the units here, you get millimeters squared times millimeters per day, and then if I multiply that, I get cubic millimeters per day. And note that a linear measurement is in millimeters, an area is square units, and a volume is in cubic units. And that is our first problem. I'll come back and do problem 2.